linear transformations are pretty fundamental objects in linear algebra. Linear algebra really is vector spaces and linear transformations. Everything else is sort of flows from those two sources. So it's worth it to know some basic properties about linear transformations, just so you know how they behave. So one basic property of a linear transformation is that any linear transformation preserves the zero vector. On the one hand, if you remember that if you have a linear transformation from Rn to Rm, that linear transformation is determined by multiplication by a matrix, then this is kind of obvious, because instead of talking about the linear transformation T, you can talk about its matrix A. What is a matrix times the zero vector? It's the zero vector, and so we're done. Notice that this is the zero vector with n entries, and this is the zero vector with m entries. But even if you don't resort to using this fact about matrices, we can still prove that any linear transformation sends the zero vector in Rn to the zero vector in Rm. And here's a nice way to do that. So if you take the zero vector, pick your favorite vector. The zero vector is that vector minus that vector. But then we can use the characteristic property of linear transformations to sort of shuffle things around like this. But that's the zero vector, except the m entry zero vector this time. So this is actually something, even if we didn't have matrices, we still would know that any linear transformation sends the zero vector to the zero vector. And in fact, one of the reasons that we have matrices is because we're in finite dimensional vector spaces. We have not and will not talk about infinite dimensional vector spaces, but they're out there, and they don't behave as nicely because you don't always have a matrix for your linear transformations. But even though in those cases you don't have a matrix, this property of linear transformations is still true. So anyway, bit of a digression. Another nice property of linear transformations is that it preserves negative. The linear transformation of a negative is the negative of the linear transformation. So what we want to do is, we want to know, is this thing, t of minus x, is it the negative of t of x? So let's add them and see if we get 0. Okay, so this time I have the minus on the inside. But by the property of linear transformations, this is t of x minus x, but that's t of 0. And we just showed that has to be 0. So there, got it right that time. Another property of linear transformations is that they preserve linear combinations. So if you have any collection of vectors and any collection of scalars, then this linear combination of those vectors, when you hit it with a transformation t, what you get is just the same linear combination, but of the transformed vectors. This is actually essentially the characteristic property of linear transformations. It's just applied over and over again to break down this big sum into individual pieces. So there's not really anything to prove here. I guess if you wanted to, you could be careful about writing out some sort of mathematical induction, and each step you tear off just the first vector, but you get the idea. One last good property of linear transformations is that linear transformations send subspaces to subspaces. So if you have a subspace in Rn, when you hit it with the transformation, it ends up being a subspace in the target space. It can't be the same subspace because these might be different. N might be different than m. They might not even be the same dimension because your linear transformation might squash down V along some dimensions, but the result over here will always be a subspace. And that's pretty straightforward to show. So suppose we have two vectors, v and w, in T of v, right? That means there are two vectors, x1 and x2, in v itself, so that t of x1 is v, and t of x2 is w. This has to be the case because remember this collection, t of capital V, what we mean by that is this is all vectors t applied to x for every x in V, right? So this is just every vector that gets hit by something in V. So if we're in this set, t of V, there must be something in V that hits it, right? So this is essentially restating the definition of t of capital V. Okay, but that means, so we have these two vectors, x1 and x2, but that means that their sum has to be in V, because V is a subspace, so it has to be closed under addition, vector addition, and that means that t of x1 plus x2 has to be in t of capital V, because again, this is just the definition of t of capital V. We had something in V, and so when you hit it with t, you end up in t of V. But t of x1 plus x2, that's t of x1 plus t of x2. That's the characteristic property of linear transformations. And so here we see that we started with, oh, and t of x1, sorry, one last thing to say. T of x1, that's V, and t of x2, that's W. Right? That's what we set up here. So we started with two vectors in here, their sum also in there. And we could play the same game with scalar multiples. I won't run through the proof, but you can imagine how it goes. So that means that this collection, t of V, is closed under vector addition and scalar multiplication, and so it is a subspace. So linear transformations send subspaces to subspaces. Let's look at some examples of using these properties. So here's a linear transformation. It's defined on a basis. So let's find t of 153. Now you might think, oh, this is a messy basis to define a linear transformation. We're going to have to go through the whole process of finding a matrix that represents t, and then we can just multiply this vector, 153, by the matrix representing t. And that would work, but that's a lot of work. So what could we do instead? Well, let's see. This vector, I actually noticed that it's just the sum of these two vectors. It was supposed to be the sum of two vectors. I think I don't want this minus sign here. For this example to work, I can't have this minus sign, right? Yeah, or I need a minus sign right here. This is how I'm going to fix this example. I need a minus sign right there. Okay, so the point here is if you happen to notice that your vector is a nice linear combination, you can skip all that work of having to work out v and w and finding the matrix that represents t. Instead, you can just write this vector as a linear combination of your basis. So let's see, it's 1 times 130 plus 1 times minus 223. Right? Turns out we don't need this basis vector at all. Then you can use the characteristic property of linear transformations. So 1 times t of 130 plus 1 times t of minus 223. And then use the values of the transformation that you know. So 1 times t of 130 is 40 minus 2. And plus 1 times t of minus 223 is 5, 6, 4. And now we can just do all the vector operations we have here. So 9, 6, 2. And we're done, right? This was, since we noticed that this input vector was a nice linear combination of these two, we didn't have to work out the whole full-blown matrix that represents the linear transformation. Of course, this won't always work, but if you happen to notice that you have a nice linear combination, then this is a great shortcut. All right, for another example, let's find the image under this linear transformation of the span of 1, 3 and 0, 1. Okay, so let's see, that's 1, 3 is right here, and 0, 1 is right here. So this linear transformation, it sends this subspace V to another subspace, right? So one way that we can write this span V is it's all linear combinations of these three vectors. These two vectors, sorry. Okay, so A1 and A2 can be any real scalar. Okay, so what does T do to this? Well, T of V is just the image of all of these vectors under the linear transformation. So A1 times 1, 3, 0 plus A2 times 0, 1, 0. But by now I hope that sort of your math intuition is screaming out to use the characteristic property of linear transformations. So this is A1 T of 1, 3, 0 plus A2 T of 0, 1, 0. A1 and A2 are any scalars. And of course, these two vectors we know, right? These are the two of the three values of T that we actually know. So T of 1, 3, 0 was 4, 0, minus 2. And T of 0, 1, 0 was 2, 1, 2. And these can be any scalars. And if you look at this, this is just the span of 4, 0, minus 2 and 2, 1, 2. This kind of makes sense, right? Because, so I guess one thing we should note is these are linearly independent, so there's no point in trying to reduce this spanning set. It's as small as it can be. It kind of makes sense that we would get the span of these because, right, what we started with was the span of these two, and what we found is that the image of this span is the span of the images, right? So it's the span of 1, 3, 0, the image of 1, 3, 0, and the image of 0, 1, 0. So this is the sort of thing that you would expect, but this is actually only true because T is linear. If T weren't linear, this wouldn't necessarily be the case. But T is linear, and so the image of the span is the span of the images, and everything is easy.